the devices or which provide the system from power losses as well as voltage well and SANs. So why we are using this UPQC? The main purpose of this device is to compensate for voltage imbalance, reactive power compensation, negative sequence current and harmonics. Actually, we are required to produce positive sequence current. So here we are, whenever you are getting the negative sequence current, then also we can compensate that problem also by using this UPQC. And one more thing, it combines the operation of the multiple devices. What are those devices? Distribution static compensator, DSTATCOM, and dynamic voltage regulator, DVR together. Earlierly, we are using these two fax devices separately to compensate the individual requirements, voltage imbalances, or as well as reactive powers or everything. So here, what the new advanced one is the combination of these two. At a time, we can regulate these two problems. Okay. And the one more thing, a UPQC is employed in a power transmission system to perform shunt and series compensation at the same time. That is the main advantage of this UPQC. A power distribution system may contain unbalanced, distortion, and even DC components. And therefore, a UPQC operates better than UPFC. That's what I'm saying. That is Unified Power Frequency Controller with all these aspects in order to provide shunt or series compensation. So here I am giving you the basic block diagram of this UPQC. So here we are injected voltage. We can use this UPQC not only on the distribution side, we can also implement for transmission system side also. And here this UPQC consists of, as I have told earlier, a series active power filter in combination with a shunt active power filter with a DC link provided in between these two. So the purpose of this series active filter is to compensate the supply voltage injected in from the primary side, that is from the supply side. And whereas the purpose of this shunt active power filter is whenever we are connecting such load to the nonlinear loads. So since we know that AC loads are nonlinear loads fluctuating time to time and minute to minute. So whenever you are connected such loads, so there will be a fluctuation in our current output, whatever the power output we are getting. So in order to compensate those voltage as well as harmonic fluctuations, we are using this shunt active power filter. And that is the basic components involved in this UPQC. So what is the total function of this UPQC we are seeing here? So the UPQC is assumed to be lossless and therefore the active power demanded by the load is equal to the active power input at PCC. So this PCC is nothing but point of common coupling. So wherever the multiple loads are connected, so we are taking that a common voltage there or common power calculations we will do. So such type of connection here we are calling it as a point of common coupling. So the UPQC provides a nearly unity power factor. So as we all know that as the power factor is increasing, the quality of active power will be increasing. Therefore, for a given load condition, the input active power at point of common coupling can be expressed in the fundamental voltage equations I have taken here in order to get the better understanding about this UPQC device. So here the voltage, line voltage is taken, that is VL as a reference voltage. So here the angle is at 0 degrees. And the load current we are taking, that is the load current is, we know some balance, there will be an angle. So that angular value we have taken as a minus phi L. There is a general calculations wherever in power electronic components, wherever you are going to do the calculations for UPQC, this is the basic design component we have to consider here. So the terminal voltage, whatever we have taken, the terminal voltage is the combination of this line voltage, or we can say the load voltage, into 1 plus K at an angle of 0 degrees, where the K represents the fluctuations of your source voltage. And it is defined as the difference between the terminal voltage as well as the line voltage with respect to line voltage. That is the factor K. Wherever we are inserting these UPQC or wherever we are using this UPQC, these are the basic voltage calculations we have to do. Now, one by one, if we are doing for series active power filter, so what are the modifications we have to do? See, the injected voltage by series active filter must be equal to VSR is equal to line voltage minus terminal voltage. And we know that here if I modify the above equation, we are getting that value is equal to minus K VL at an angle of 0 degrees. Small voltage modifications we have to do. If we are simplifying that equation, we will get the final equation as minus K VL at an angle of 0 degrees. So here, whenever you are going for power calculations, the UPQC, again it is a lossless one, the power input at PCC, the UPQC provides a nearly unity power factor from source current. Therefore, for a given load conditions, the active power, so previously we have seen for voltage, now we are seeing for active power. As I have earlier repeated, and the same thing here I have mentioned, it provides us the active power at the point of common coupling and compensating the power factor and improving the power factor to unity. So we are calling here, we are taking it as the terminal power, whatever we are getting, that is almost equal to our load power PL. When the line is connected as a lossless line. Okay. Now, so in generally we know the power equation P is equal to VI. So terminal voltage and source current. And PL is the load power. Whenever you are going for the load side, you will get a power factor there. And that power factor is VL IL cos phi L. Now, if I substitute this VT, terminal voltage from the previous equation, I will get VL into 1 plus K and put that IS as it is. Then VL IL cos phi L. If we modify that equation, here at the right side, I have given the total source current equation. So what is that source current is equal to IL cos phi L by 1 plus K. These VL and VL get cancelled and we will get the source current IS value. Then the complex power. So whatever the general power what we are receiving, that is our apparent power. We all know that apparent power is the combination of active and reactive power. And here by injecting this UPQC device, we are compensating reactive power. That is also one more advantage of this device. So compensation of reactive power means increasing the active power value that gives you the continuity of supply. Okay, so here the complex power of series active power filter is expressed as SCSR is the representation of phasor representation of series active power filter complex power. And it is a combination of VSR complex value as I know. We know that IS conjugate value. If I split that equation, VSR IS cos phi S. Why we are taking only the active power? Already I have told. The active power is the leading component compared to the reactive power. Here I have also given the reactive power equation also. So these equations, wherever we are getting VSR, so earlier we have done for VSR that is equal to minus K VL and put that IS as it is and cos phi S. That is the active power. And opposite to that is your reactive power. VSR IS sin phi S. That is the reactive power component. Okay, so since if we assume that phi S is equal to 0, why we are taking phi S is equal to 0? Because unity power factor means power factor is defined as the cos phi. If the angle phi is 0, then cos phi is the leading value. Then your power factor will be unity. So whenever you are injecting this UPQC device, so your phi angle will be equal to 0. Then you are maintaining unity power factor and your active power will become, if cos phi S is equal to 0, your active power will become minus K VL IS. And the reactive power, obviously we know that sin phi S is 0. Then QSR will be, that is the reactive power of series active power filter will be equal to 0. That is the concept of calculating the fundamental values whenever we are injecting the series active power filter. The same thing we'll do for shunt active power filters. For SH is the shunt active power filter with a combination of line voltage VL and shunt current IS, H its conjugate value. Now the current provided by the shunt active power filter is the difference between the input source current and the load current, which includes the load harmonics current and the reactive current. Therefore, we can write this difference equation as ISH is equal to IS minus IL. And we know that IS is the source value. Then we are taking the angle at a source, we are taking the reference angle as 0 degrees minus IL at an angle of minus phi L. Again, ISH is equal to, if we substitute the values of IL there, I'm getting IS minus IL cos phi L minus JIL sin phi L. Where we got this? Just we have converted this polar form into the rectangular form. Polar value is converted into rectangular value. There we got the value IL cos phi L minus JIL sin phi L. So if we separate the real and imaginary terms, I'm getting the value IS minus IL cos phi L plus JIL sin phi L. Again, the shunt power is the combination of VL, load voltage, ISH cos phi SH, and that is equal to VL into, instead of ISH, I am substituting the value IS minus IL cos phi L, and separating the real part to the active power component and imaginary part to the reactive power component. PSH and QSH, where QSH is equal to VL ISH sin phi SH, and that is equated to the VL IL sin phi L. Here also we have separated in the shunt active power filter the active power component and reactive power component. So the basic line model of the active power filter. So after doing all these calculations for the given 4-bus system or 12-bus system or any 32-bus system, for any different types of voltages, 11 kV or 120 or 66 kV bus systems or 132 kV bus system, whether in distribution side or whether in transmission side, these are the basic calculations you have to do. So after doing that, this is a simple line model for the series active filter. Wherever we are going to connect, we have to consider all these. So whatever the calculations we have done earlier, the same we have to inject here. And one inverter we are taking with a series, that is with a capacitor. That capacitor value will be depends upon the device where we are connecting. So this is the utility grid. So from the utility side, we are taking VS and IS, and there the controller we have used here. And from that voltage controller, a PWM pulse width modulation technique is used, and it is injected to the inverter. Then it is a capacitor is acting as a battery, and it is again refed to our load terminals. Non-linear load. As I have already told, for the AC systems, most of the loads are fluctuating load. So we are considering here non-linear loads. So whatever the basic operations I have told, the same thing I have mentioned here. The series active filter is connected in series with the utility grid through a coupling transformer. By inserting a series active filter between the AC source and the nonlinear loads, elimination of voltage harmonic components on the load side is achieved. This is the main target what we have to do. We can do by using the series active filter. This is achieved. How we are harmonics, how we are reducing, that I have given. This is achieved by injecting voltage harmonics components across the coupling transformers into utility grid. Series active filters are operated mainly as a voltage regulator and harmonic isolator between nonlinear load and the grid. This type of approach is especially recommended for compensation of voltage unbalances and voltage sags from the AC supply. So the series active power filter injects a voltage fundamental component in series with the supply voltage, and consequently can be regarded as a controlled voltage source, compensating voltage sags and swells on the load side. This is a Simulink model, what we have to design in the simulation. So whatever the types of IGBT switches we have taken here, with the series filter and VL values, this is the Simulink model for series active filter. The basic model of this shunt active filter is here. Again, whatever the PWM controller technique we have taken in the series filter, the same is implemented here. And the active filter controller output is fed to our load side to compensate the fluctuating load current. And the inductor here L acts as a filter. The same here, the implementation, how we are using that we have given. A shunt active filter operates as a current source device, injecting the harmonic component generated by the load current, but 180 degrees phase shift. Since there we have used the PWM technique, we have taken the phase shift of 180 degrees. So the nonlinear load may be considered as an AC motor driven by a voltage source PWM inverter. The shunt active filter with or without transformer is connected in parallel with the load producing harmonics. So we can take here series active filter, or we can take here with the transformer or without transformer. Both we can consider here. If we want to regulate the voltage at the load side, then we will connect a transformer to step up or step down. If you want to fix up the voltage as it is, no need of connecting the transformer. This is the basic simulation model of our shunt active filter. So simulating model is given here. Coupling inductor, current, PI controller is used, DC voltage which is fed from the DC to DC link, and the line to line current, compensating current calculations will be done. And hysteresis band controller is used here. Why we are using this hysteresis band controller? Because general frequency of our AC supply is 50 Hz. So in order to increase the value of your frequency, we are using here hysteresis band controller. Wherever the load fluctuates, all the parameters will vary. Rather than voltage and current, all the frequency components, time components, impedance, admittance, every values will be varied. So at that case, the frequency plays a major role. In order to compensate that frequency modification or frequency fluctuation, we are using this hysteresis band controller. So generally what I have repeated voltage and current harmonics here. If I take the voltage, the upper one figure shows the voltage harmonic. A simple line model calculation we have taken with the distribution side. So here, if you see the waveform of that voltage modification from 0.9 to 1 second, there is a variation of our voltage fluctuation. And similarly, there is a variation in the current harmonics. The bottom figure indicates the current harmonics and the top one indicates the voltage harmonics. So these variations taken from 1 second, 0.9 to 1. That time duration is calculated, and here we have to check the active power filter as well as shunt filter. Series active power filter voltage should be injected here. Then we can reduce here these harmonic content values. So whenever we are going for analysis, here a simple result oriented I have kept for better understanding. Whenever we are using this UPQC, is the result based on a system where we have used 400 volt phase angle with a 0 degree phase angle and 50 Hz frequency. So for such type of a grid system, I have taken 50 at the distribution side and we have calculated the result. So there we got without UPQC from 0.9 to 1 second. See the current voltage variation. Whenever we have done the analysis here, for a fundamental frequency of 50 Hz, total harmonic distortion here we got 22.41% without UPQC. Okay, so when I have used the UPQC, here I have taken signal from the same value 0.9 to 1. See the previous one, there is a lot of fluctuation in the voltage signal there, as well as the effective value, the total harmonic distortion is 22.41%. Again, if I am using this UPQC, total harmonic distortion, the sinusoidal pulse is regulated, the harmonics are reduced, and this total harmonic rate, whenever we have done with FFT analysis, fast Fourier transform analysis, for the same constant frequency of 50 Hz with the same duration of intervals, here we have reduced the 22% to 2% value. This is, there is a lot of change in our total harmonic distortions we got there, where we have used this UPQC device. Okay. So what I want to conclude is, a power system has been modeled earlier, whatever I have done in the previous one, by using the MATLAB and simulating. From the simulation results, we have observed that UPQC is capable of compensating voltage sag and swell, and so current harmonics very effective. Furthermore, the total harmonic content is reduced from 22.41% to 2.15%. So it is concluded that series connected active filter is compensating the voltage distortion, and current harmonics are effectively suppressed by shunt connected filter. That's what I want to discuss. That is, what is the device UPQC concept, and what are the main parts of that UPQC, and what is the advantage of that UPQC whenever we are using a transmission side or as well as the distribution side. So whatever the example I have taken, I am taking for 400 volt, 50 frequency to reduce the 7th harmonic. These result analysis are less than 7th harmonic in the distribution side. So there I got different implementations. So whatever the facts even we are using, so the better one to select, and the, comparatively the previous one is the somewhat flexible. There is somewhat flexible operations. You know that the simple calculations we have the fundamental AC calculation to connect the series filter as well as shunt active power. The basic thing what we have to observe here is, whenever we are going to connect the point of common coupling. So what the term itself, the point of common coupling means, whenever there is a fluctuation in loads, then multiple fluctuations are occurring, there we have to maintain a common voltage and current without changing frequency. So in order to eradicate that frequency problem also, we have used the hysteresis controller.
Thank you, madam,
Thank
for
you.
your nice presentation, madam. On
Thank you, sir. Thank you for
yes, madam. Series active filters and shunt active filters combination, and how we can improve the performance of the system by reducing the harmonic distortions. So thank you very much, madam. So participants, if you have any doubt, please rise. Have any doubts? Yes. So once again, I thank you, madam. I thank all
Thank
the
you very much,
participants.
sir.
Yes, madam. Thank you. I
Thank
thank
you for
all the
giving me this
participants.
opportunity, sir.
Okay, madam. Thank you, madam.
Thank you.
I thank
Thank
all
you,
the
Vinita.
participants for so the attending this faculty lecture series continuously. So thank you. With this, I will close the today's session. Thank you. Thank you, madam.
Thank you, sir.